So the topic that I can talk today is about the airport, international airport. They call U-Tapao Airport. This work has been finished within this phase, and then they still continue the next phase of the construction. And the work, the owner is the Royal Thai Navy, and the main contractor is Plan Engineering, in which we have the designer, which is the IEC, International Engineering Consulting, and also the consulting. Another consulting is the Index, International Decade and Span. And the work that I'm presenting here is the work that done by Geo Harbor Construction. Okay. So let's see the general information of the project. As you may know that Bangkok and vicinity area, we have two international airports, which is the Suvarnabhumi Airport and Dongmueang Airport. Okay, and then since the government is trying to expand the economic corridor in the eastern part, and then there's a necessity that we need to have the international airport in the eastern part, in which there's already a military airport over here, and then they improve it to be the international airport and expand it to be able to take the more capacity of the flight. This is the location of the U-Tapao International Airport over here in the eastern part. Let's see the overall layout of the part that that I'm gonna show the information today. This is the location. This is the area that in the color that has been improved by dynamic compaction in several techniques. Because in general we call dynamic compaction, which can be a different techniques that I will discuss later on. In this area, we have the RIC in the yellow color. RIC is a rapid impact compaction, which said to be the primary technique that to be used in this area. And the second method that used in this area is a HVDM, which is in the blue color, which is some kind of expand out from the RIC. Okay, this is the taxiway area, taxiway KU and so on, and this is the runway. Okay, the total square meter is about 670,000 square meter area that have to be improved. General soil conditions. This is the data from CPT. You can get very quick information from CPT, especially the classification of soil without needing to go to the lab. Okay, and this is why we have they had several CPT locations that have been done. In this red zone, you can see. By the way, this is the zone that might be in the future going to be some building, so that's why there is no improvement. Okay, so in the red zone here, you can see generally on the very top of the layer, we have sandy material. We have sand, silty sand, sandy silt and silt, those kind of things. The depth is generally about 1 to 2 meters. Okay, that we find most of the sands here. But below, we start to see some clays, as you can see here, clays. Okay, and then the clay layer mix together with sand, and then the improvement depth that required by the owner, by the designer, is about 6 meters. Okay, so you can see that for the whole 6 meters, we have some kind of mixed material. Okay, between sands and some clay, some silt, and groundwater table also quite high. It's about 1.5 minus 1.5 to 2 meter, and some area maybe minus 2.5, something like that. Let's see some other area. This is the area of the runway. And this is the same thing on the top, on the very top of the layer here, about 1 meter or 1.5 meter, you have sandy material, most of sand, but below more clays. And then in the south area of the runway here, you can see, most of the material are clay. Now, when we like to improve the material, of course, this sand, I forgot to mention, this sand are loose and into the medium dense state, but mostly are loose sand. And then the loose sand very loose on the top, and then also about 5 to 6 meter also present some of the loose material as well. As for clay, the stiffness of clay in this is range from some area with high groundwater table. It would be like in soft clay, not too soft like Bangkok soft clay, but still soft. And then, but generally is going to be in the range of the medium stiff, and some area, if it's dry, it's going to be very stiff. Okay, and this is the northern area of the runway. You can see the similar trend of the deposit over here, and this is the taxiway. Some area you can see that there is no clay at all. For the whole 6 meter, they are all sands. Okay, and so on. Now, thinking about the method to improve, because this is going to be used for runway pavement for the taxiway, and then what should we worry about this one? We should worry about the loose material that present here. That one thing. The second thing is we should worry about the consolidation settlement or long-term settlement if the load is quite large. But luckily, the load that apply, okay, the pavement load, and comparing to the strength of soil, even though the clay is not that soft, so the consolidation or long-term settlement would not be expect much in this area because it's not soft clay. Okay, but the problem is the loose sand, loose material. Okay, that can have the problem with the structure of the pavement itself. I mean the runway pavement, if you have the loose material below. Okay, so the dynamic compaction is option to be used. Let's see what is the dynamic compaction. Generally, the basic concept of the dynamic compaction to be used for the loose, to densify the loose granular and sometimes the mixed soil, but mostly should be granular material, and it's going to be used improved by using the dropping the heavy weight hammer like this to the certain height. Okay, the weight in this is from 10 to 15 tons, and then the height could be up to about 10 meter or more than that, and the drop can be done in several parts. Generally, it's about 2 or 3 passes in the same footprint area, the same drop area. Okay, and this is the suitability of the dynamic compaction for soil type. As I already mentioned, is excellent for the granular material. Okay, and then 0% of the fine material is perfect. No matter the saturation high or low. And then it will less effective if percentage of the fine content is getting higher, and also the plastic index is getting higher. Okay, of course, for the organic material, okay, or some of the clay that have the plastic index over than 8, and then with high water table, this is not recommended. Yeah? In which you can see that in our site, we also have this kind of clay layer. However, that is not our target because as I already mentioned, the stiffness of those clays is not that soft. It's in the medium stiff, some soft, but in the upper bound of the softness of the shear strength. Okay, so generally we can use dynamic compaction for this site because it's a granular material. Okay, semi permeable soil deposits also like silty material and sand, something like that. Silty sand. Okay. By the way, the energy from the drop weight will transfer or transmit into the deeper layer. For the case of the dynamic compaction, of course, the higher the drop height and the bigger the weight, the improvement depth going to be deeper. Okay, and then this can go down to about 6 to 10 meter for the maximum improvement depth. Okay, and this is how it looks like. Okay, this is the grid of the improvement, and then in each area there are going to be 2 or 3 passes of the drop. After the drop, they're going to leave the crater like this, in which they need to be refilled with the granular material. Okay. All right, and the influence of the dynamic compaction generally would be according to this equation. This is the general equation. It's a square root of weight and height. Okay, that drop, that which is the energy. Okay, with some constant value over here. Okay, so this is the correlation between the depth of influence and also square root of energy, WH. And it depends on the material on the soils, like dense soil, loose soil, something like that, loose sand. Okay, and then the depth of influence, as I already mentioned, is up to about 10 meter and less effective to the 15 meter. Okay. That's the first method of the dynamic compaction. However, in some area, there might be a difficulty in getting a big equipment like that, big machine like that, or big drop, or even some of the area that require some environmental restriction. The heavy drop like that may be minimized. Or otherwise, it may not be necessary to go that deep for the influence depth of the improvement. Maybe we need more shallow improvement like this one. Okay, this is called rapid impact compaction, which is suitable for the not too deep compaction layer. I mean compaction depth. Okay, so this is the basically the weight here is lighter than the dynamic compaction. Okay, the drop height is shorter, of course, but the energy could be the same by using the number of blows, which is more than the faster rate comparing to the dynamic compaction. The rate is about 40 to 60 drops per minute, in which dynamic compaction is more than that. Okay. All right. We're going to talk about the component of RIC later on, but generally it's include of the impact foot or anvil, the driving cap, and also the hammer. Okay, I'm going to show the picture later on. Oh, by the way, it's over here. Okay, this is the anvil or foot. This is the driving cap. This is the hammer. So the hammer drop into the foot or anvil. Okay, not directly to the soil. Okay, so this one is the one that transfer the load or energy to the ground. Okay, all right. IC can become a midden depth soil improvement, which fill the gap between if we're not going to use the dynamic compaction and if we're going to use just the roller compaction, this is very shallow. Okay, in a few centimeter, but RIC will fill the gap between roller compaction and dynamic compaction. This will be between 5 or 6 meter as a maximum depth that it can go. Okay. All right. This is the photo of the actual machine that used. So you can see that is the size of the machine comparing to the dynamic compaction is a little bit is quite smaller. So it's suitable for that. The drop weight is about 5 to 6 tons, depending on the size of the machine, of course. And then the drop height is about 1.2 meter, 1 to 1.2 meter. And the rate, as I already mentioned, the diameter of the foot or anvil here is about 1.5 meter. Okay. And then you can see the comparison here. Okay. The range of the depth of compaction for the static rolling or roller is about 20 to 50 centimeter only. Okay, the dynamic roller can go a little bit deeper, 40 to 1 meter, 40 centimeter to 1 meter. For RIC, it can go down to about 4 to 6 meter, 4.5 to 6.5 meter, but also depends on the condition of the soil itself. If it's granular and dry, it can perhaps it can go deeper. But for dynamic compaction, the maximum it can reach for about 10 to 14 meter. But of course, this depends. Everything depends on the material that we do the compaction. Okay, let's show some video. Okay, you can see that the anvil or the foot is the one that penetrates into the ground. Okay, and then the drop weight just drop directly to the anvil, to the foot. Okay. Seems like quite a boring job if you need to supervise this kind of work. You need to hear a lot of noise every day, all the day. So this is the depth of the improvement of the RIC, the same equation, okay, but just include the number of blows because this is different. Actually, for the dynamic compaction, you also need to have NB as well. If one location need to have 2 or 3 blows, okay, and then this is the constant value, okay, and square root as well. Okay, this is generally the same equation, the similar equation of the dynamic compaction. Okay, and this is the workflow. Yeah. Before we do the ground improvement, actually whatever ground improvement, we need to do the site investigation before to check the existing condition. So in this case, we use CPT. Okay. And then the first sequence has been done. Okay, the first sequence like this, and followed by the to check the effectiveness of the first sequence. We can do the CPT after the first sequence, and then the second sequence like this. Okay, and of course later on the CPT at the location where the drop has been dropped, and also the location where there is no drop at all. Okay, and see the improvement, how it's going to be like. For this site, we have done some tryout section in which I'm going to discuss later on. Okay, and then this is the setup of the tryout section that we use the 2 phases. Okay, the first phase, the spacing is 6 meter, and then the second phase is 3 meter. The first phase is designed to go deep, about 6 meter, and then the second phase is to fill the gap between the first phase. Okay, and then the RIC machine that we use is 9 tons. Okay, and with 2 tons steel foot. Okay, and then there's some limitation or the termination of the improvement in which I will discuss later on. Okay. Oh, by the way, the weight of the RIC itself is about 60 tons. 60 tons. Okay. This is how we terminate each location okay, is either by um, by um, by each limitation here. If the blow that are going to be implement should not more than 30 blows. Okay, that's one thing. If it's more than that, the soil is very soft. Okay, and the termination can be terminated if the final settlement is less than 8 millimeter. Okay, that's the second criteria. And the third criteria is if the anvil or the foot is all. I mean, if the drop this travel distance is longer than or more than 80 centimeter, which is longer than the height of the anvil that we need to stop. So this is this kind of the limitation of the machine, by the way. Okay, and but generally this is what we want. Okay, we want that for the last blow, the settlement should be low. Yeah. Okay, and dynamic compaction or RIC would present the same behavior. Okay, that whenever that you drop, the hammer into the ground, the excess power pressure will increase, and then the decrease or the dissipation of the excess power pressure is depends on the permeability of the soil that we improve. Okay, so this kind of curve can be expected that, for example, this is the first blow, second blow, the first phase, second phase, and third phase. And you can see that this is depend on the depth, 2 meter to 3.5 meter and 5 meter. Okay, 5 meter is up here. Okay, and this is the pore water pressure. Okay, and then you can see that some soil, some depth, the dissipation is very good. This one very good. Okay, but for the third phase, because there might be some accumulation from the first and second. Okay, so you can see that the dissipation is a little bit longer. Okay, now the problem of the dissipation rate has also affect the construction time. Imagine that if we deal with not so pervious soil, okay, not so granular and clean sand. If we have some silt, some fine particles that mix into the granular soil, the dissipation rate will be slower. Okay, and if the dissipation rate is lower, we need to wait because if we still blowing when there is a high excess pore water pressure, there going to be not much of the improvement. Okay, because excess pore water pressure is try to cancel out the energy that you apply, and then the energy that you apply more will increase more excess pore water pressure, which is not good. And also it's not good for the machine as well, because when you have build up in excess pore water pressure, there's a possibility, okay, that heavy machine can sink down because of the shear strength is temporarily reduced. Okay, so that's why there's a third method here that called dynamic compaction again. Okay, but this is with the high vacuum pressure. Okay, they call the high vacuum dynamic method, or HVDM. This is basically try to accelerate the process of the dissipation. Okay, and it can be used for not so clean soil. Okay, not so clean soil where excess pore water pressure may be built up higher, and dissipation rate may be slow. Okay, so this method combine dynamic compaction and vacuum dewatering technique to improve the saturated fine sand and also some sand material. Okay, fine clay and fine sand as well. They apply the negative pressure, maybe not like a vacuum consolidation, in which vacuum consolidation or VCM is in the airtight environment because they use the membrane in order to make it airtight, and then negative pressure is fully developed. But in this case, it's a mixed technique between dewatering and also some vacuum. vacuum pressure may be effective in the layer that we have clay, okay, but not much of the vacuum pressure will be effect in the layer that we have sand. But in sand, they can do the dewatering in order to reduce the water table. And of course, when water table reduce, the degree of saturation reduce as well. Okay, that's the main thing of the high vacuum pressure. Okay, and this is how HVDM looks like. Okay, you can see that this is the series of pipe. I mean the drainage pipe that need to be installed into the ground with the close spacings, and then they need to leave some space between the row of pipes in order to develop the excess pore water pressure by dynamic compaction. Okay, and then the question is, can RIC be done in this as well? It's possible to use RIC together with the HDVM, but the problem is the energy of RIC is not as large as the energy of the dynamic compaction, especially if we're considering the energy that will be transferred into the sideway. Okay, RIC may have some limitation in the horizontal dissipation of energy. Okay, but dynamic compaction can go very wide. So that's why it means that we can have the wider row of pipe if we use dynamic compaction. Okay, it's going to be like this. Okay. All right. Okay, that's the same. In this project, since we have some kind of mixed material, we have the area that is 100% sand, okay, from the top to the bottom, as I already mentioned, but not much. We have the target that, the 1 to 2 meter or 3 meter of loose sand that we need to, improve, which can be done by the RIC, okay, and we also need to improve the material that mix between sands and clay and some silt, which may have the fine particles, which can create the excess pore water pressure. So that's why in this project we use three techniques: dynamic compaction, and then RIC, and also HVDM. Okay. For the HDVM, the dynamic compaction machine that they use is 14 ton of drop hammer, and the height is about 10 meter. Okay, and then and in each drop, in each location has 3 passes. Okay. We have some trial area for RIC and also for HVDM. This is the trial area in the HVDM. But generally, the setup of the pipe going to be like this. Okay, we need to excavate some kind of small canal in order to control the surface water that may be flow into this area in the test area, and then in the perimeter of the test site over here, the longer drainage pipe, 6 meter, is installed at the edge here, just to control everything, control the boundary, the groundwater from outside and groundwater from inside. But the blue color here that you can see here is location of the shorter drainage pipe, 3 meter, okay, with some spacing that you can see here. Okay. And then trial area, we have 2 trial area for the HVDM, 71 and 78. Okay, and this 78 is a little bit different from the previous one, because the deep pipe and the shallow pipe is installed together. This is just to see the effectiveness, okay, of the vacuum pressure. Okay, so that's why we have to do trial area, okay, in order to make decision that way how we're going to install the pipe. Okay. All right, this is just the workflow, the construction workflow monitoring and CPT test before and after. As I already mentioned, HDBM starting with the working platform. Okay, and then the important thing is to calculate the safety of the machine because of the load that apply to the loose sand, to the loose ground, and then can have the problem of the bearing capacity. So that's why the working platform has to be thick enough in order to control that. More than that, working platform need to provide some normal stress to the ground in order to control the power to pressure ratio because the machine need to be there and then apply some energy to increase the excess power to pressure. If the excess power to pressure is high and then we don't have some kind of normal stress to control or the surcharge to control, that could have some kind of soft foundation. So in this matter, working platform has two purpose, not only one. Not just like in the VCM also in VCM, as Professor Bergado mentioned that the working platform or the surcharge actually used as a platform for the PVD installation, and also the surcharge or the working platform can be used as the drainage layer as well for the VCM. And for the construction sequences, we have step 1, install the drain, which is not prefabricate that vertical drain. This is just the pipe, just the steel pipe. Okay, and then that covered by the filter, by the fabric filter. Okay, install. Okay, and then after that, do the compaction in sequence. We have 2 sequences. Okay, start by turning on the vacuum pump. Okay, and then later on dynamic compaction. Okay, and for the monitoring that generally have, but especially in this tryout section, we have observation well, we have the piezometer, of course, that's necessary, elevation measurement, but this is not just the surface settlement, but the multi-point surface settlement, okay, in order to see the settlement in different layers, okay, and then and in each compaction phase, the settlement in the surface at the crater need to be monitored as well. For the strength test, CPT before, and then as I already mentioned, during and after. Okay, this is how to install how the construction sequence of the HVDM. Okay, the pipe installation. Okay, the drop weight. Okay, and second phase. Okay, and then the install. This is the some photo, not from this site. This is what the photo we got from Geo Harbor of the other works. Okay, but the same technique. Okay, this is the installation of the pipe. Generally use this kind of like screw, like auger. Okay, like a fly auger in order to make a hole and then just install the pipe. Yeah. And this is the dynamic compaction. Okay, dynamic compaction, the first sequence, the second sequence. Okay, and then these are the monitoring equipment. Okay, and this is the crater, how crater looks like. This is at the site of U-Tapao Airport. SPT, soil boring, CPT, and also we also add SASW, which is the determination of the shear wave velocity, because as I already mentioned, this site is quite vary in terms of the soil layers. So that's why we also need some other technique in order to characterize the soil profile. And this is the field instrumentation for RIC tryout section, HVDM. Okay, the same depth of the piezometer. Okay, and then in different locations. Okay. 2, 4, and 6. And this is the location of the tryout section for the HVDM and for RIC. Okay. This is the result. This is the pure information of the excess power water pressure from the piezometer. Okay, and then you can see that generally it's difficult to to analyze that which one is more effective, because basically two methods have different energy applied. So that's why we need to calculate what was the energy applied for each technique. Okay, HVDM and also RIC has a different energy. So that's why we calculate energy, and then we use the energy to normalize excess power water pressure. Now it seems makes sense. Okay, this is the normalized excess power water pressure by the cumulative energy, and then this is the time. And you can see that the orange color lies here from RIC, and the blue one from the HVDM. Even though HVDM, they use the bigger hammer, okay, higher energy, but because of the vacuum pressure, so that's why even though the excess power water pressure is high at the beginning, I come back here, the maximum excess power water pressure is quite high comparing to the RIC. In some depth, it's similar, especially shallow depth, but in deeper depth, it's quite different anyway. Okay, but you can see the dissipation is significant different. Okay, for RIC, which is no vacuum pressure, okay, you can see that the dissipation is quite taking some time. Okay, but as this one, the dissipation is fast. Okay, what does it mean? If the dissipation fast, the soil will not lose too much of the shear strength, temporary losing of the shear strength because of the excess power water pressure increase. And then it means that for the HVDM, the workflow can advance faster comparing to RIC in this general. And as Professor Bergado said, time is money. So that's why in some area that we have lots of clay layer, HVDM is more appropriate. Okay, but of course, in some area that we not is not necessary to use HVDM. For example, the area that we have the granular material, okay, and then there is no dirty material like fine contents. To use DC or RIC is faster because there are also no time of installation and de-installation of the vacuum pipe. Okay, all right. This is the normalized excess power water pressure dissipation of the RIC and HVDM. So we use the maximum excess power water pressure to normalize, okay, and to see the dissipation. The same thing here, but you can see more clearly about the depth. Okay, for the HVDM at 6 meter, excess power water pressure initially high, but it dissipates very fast. Okay, and then so on. Okay, this is the excess power water pressure ratio. Okay, and then and also the cumulative energy of RIC and HVDM. This is another important parameter to check. Power water pressure ratio, if it's more than 1, it's not good, of course. It means that the excess power water pressure is actually more than effective stress. It could have the problem of boiling, or it could have the problem to the weight of the machine that apply. Okay, you can see for the RIC, there are several locations, especially in the shallow depth, that the power water pressure ratio is higher than 1. Okay, for the HVDM, since they use the dynamic compaction, energy is quite large. So several drop. Yeah, the first drop, second drop in some area is actually higher than 1, and then some also quite near to the 1 to 1.0. Okay, so this could have a problem to the machine that used for the RIC and also for the HVDM. So that's why, as I already mentioned, we need to design the platform. The platform work as increase the bearing capacity of for the machine, which is about 16 tons for the RIC. And then, but more than that, when we have the platform, they also reduce the power to pressure ratio. Okay, this is the second benefit, which is in this case is more benefit. It's very good benefit in order to prevent, the softness of the soil during the construction. Okay, this is the calculation to show the bearing capacity and then also the thickness of the platform. And once we use the platform, we found that the power to pressure ratio reduced into some of the range that is quite safe to perform. Okay. All right, and this is the effective depth of the improvement for the HVDM. Similar equation anyway, should be similar to dynamic compaction, right? Because it's the same concept, but it's just as the vacuum pressure, that's all. Okay, so you can think about having the vacuum pressure HVDM and dynamic compaction. You can compare between PVD preloading and also the preloading technique in the soft clay. It's pretty much similar. Preloading with no acceleration of the settlement, and preloading with PVD with the acceleration of the settlement. The same thing as the dynamic compaction without any accelerate of reducing of the excess power to pressure comparing to HVDM. Okay, and you're quite curious that what is the effective, horizontal distance from the RIC and HVDM, which is the dynamic compaction. So that's why the information of the piezometer has been plot over here, okay, with different technique and different depth. This is 2 meter, 4 meter, and 6 meter. Okay, but generally you can see that the effective radius or distance is about like 3 to 4 meter. Okay, 2 to 4 meter, no matter whatever type, but seem to be HVDM is a little bit longer, larger, because it's a dynamic compaction. Basically, it depends on the energy applied. Totally depends on that. Okay. Finally, this is the final slide that I have here. We assess the effectiveness of 3 methods by using the cone penetration, as you can see here, and then this is the RIC, HVDM, and DC. Okay. We cannot really compare because each technique was selected depends on the different type of soil profile. Okay, but generally all the methods can be improved. Can improve the strength, the QC value, the tip resistance of the cone. Okay, or the shear strength increase. Okay, for RIC, for HVDM, you can see here before and after. And for the dynamic compaction alone, which is in the area where we have only sands, okay, only granular material also increase. Okay. Conclusion: the effectiveness of HVDM method over RIC method, we can see some effectiveness, but we cannot say that it's more effective. But it's because it depends on the soil type anyway. Okay, but the advantage of HVDM is they can reduce the excess power to pressure and also can reduce the groundwater table. That's another thing. Okay. The dissipation rate made by HVDM method is faster, of course, because there's a vacuum, even with using the high energy compact by the RIC. comparing to the RIC. RIC method also has its limitation regarding the waiting period. This is already discussed for the excess orbital pressure to dissipate. Okay, because of the sufficient bearing capacity is essential to keep RIC machine above ground surface. Okay, that's all for my information. Thank you very much.
Thank you very much, Dr. Suttisak. Okay, the very interesting talk, and you talk about the comparison of your HVDM and other methods and so on. So, do we have any questions for Dr. Suttisak? Okay, I am seeing one question on the chat box. Dr. Suttisak, you can read it, or you want me to read it to you?
Okay, I can read it here. How can we control the effects to the nearby structures by doing HVDM? What are the practical difficulty when we do HVDM and how to cope with it? Luckily, this kind of, vibrate method, like dynamic compaction, is generally be allowed to use in some of the rural area. Not in the in the city or in the but anyway, if there is some structure that nearby, as I already mentioned, for the effect from the drop weight, I think that there should be two effects. The first is the effect from the vibration of the drop weight. That one thing. Okay. Generally, we need to check, because each type of soil there are different shear wave velocity. But we need to check that how much or how long of the distance that will be less effect to the nearby structure. Okay, this can be done by just measuring the acceleration with the distance directly at the site. I think that is recommended. Or otherwise, you can do some simulation that can be done as well. The second effect is the effect that there might be some lateral inward movement, just like VCM. Okay, but just like I mentioned, that it's not the vacuum pressure that we use and vacuum technique that we use cannot 100% compare to the VCM method in the soft clay, because it's not totally airtight system. So that's why not much of the inward lateral movement that we can see. Okay. The second thing is, the second question, what is the major geotechnical design criteria of the project? That is very good question. Okay, the criteria from the designer is to improve the 6-meter subsoil. Okay, to have the CBR value more than about 8%. Okay, that basically that the design criteria for the transportation system, right? For the embankment and runway, something like that. Okay, and then we need to convert the CBR 8% into our CPT strength, in which I cannot remember that how much it's going to be, but we need to convert that. And luckily, some of the soil layer that we worry, for example, like clay. Since it's not that soft, the stiffness is start from medium stiff to stiff, and especially if it's dry. So that's why initially CBR is already very high. Okay, the problem is the loose sand above and loose sand below the clay. We also have loose sand. That's the problem, and in between. That's the thing that is difficult to treat, and it even more difficult if you think about in terms of the modeling, because if you apply some vibration from the top, and the vibration wave pass through the granular material, which is no problem. It's just go through, but when it go through the clay layer, there has a lot of damping. So that's why the energy can be dissipated or absorbed by the damping of the clay. So that's why what we worry is about the loose sand that below the clay layer or in between the clay layer. That would be the problem. Okay.
Thank you. All right, we just got another question here.
Okay. Can we use dynamic compaction in the area having high groundwater table, like area is highly susceptible to liquefaction. Yes, we can use that. As I already mentioned, dynamic compaction can be used if the soil is granular and then clean. In which, if you discuss about liquefaction, of course, liquefiable soil need to be clean sand. This is perfect match that we can use this, and it means that every drop that we drop, even though pore water pressure increase, but it will be dissipated very fast with no problem.
Okay. Is there any question? Here we got another.
Okay. What will be there in pore water pressure analysis if we use vertical PVD in place of vertical pipe? Oh, that's interesting. First of all, we cannot install PVD in the sand. That's the problem. That's the first problem. But if we could, oh, that would be interesting. That would be interesting. I don't know. I have no idea. But that I think the effect would be the same in the model. In the model, it would be the same. Because it depends on what? It depends on the perimeter of the drain area, right? Okay, so we can compare to the perimeter of the pipe and perimeter of the PVD shape. Okay, and the area of the drain. Maybe from my thinking, I think the drain pipe would have more effective well area comparing to the PVD. Okay, and the reason that we use PVD for the soft clay, because it have the longer or wider in order to be able to get more surface area for the drain, right? I think that would be the reason.
Okay. Well, it's thank you very much. Oh wait, we got another one to see.
Can we apply HVDM in reclamation project for residential? Wow, and or housing project, even though the subsoil condition is composed of marine clay and silty clay? I would not recommend. I would recommend go directly to VCM or PVD with preloading. That would be more appropriate.
Yeah.